Uranus, the seventh planet from the Sun, has always fascinated astronomers with its peculiarities. It stands out as one of the most unconventional planets in the solar system, with characteristics that defy what we consider normal for a celestial body. From its lateral tilt to its unique atmospheric behavior, Uranus presents mysteries that continue to puzzle scientists. Recently, one of these mysteries, the steady cooling of its upper atmosphere, has finally begun to reveal its secrets, and the answers are as fascinating as the planet itself. A planet of extremes. To understand Uranus, we must first appreciate how fundamentally different it is from other planets in the solar system. Unlike Earth, Mars, or Jupiter, whose axes of rotation are relatively upright compared to their orbits, Uranus rotates on its side, tilted at a dramatic angle of 98 degrees. This extreme tilt is probably the result of a massive collision with another object billions of years ago. The impact was so catastrophic that it left Uranus essentially lying down in its orbit, with one pole pointing directly at the Sun for part of its 84-year orbit. Adding to its oddity is Uranus's retrograde rotation, which means it spins in the opposite direction to most planets. This combination of extreme tilt and retrograde spin creates seasons and atmospheric dynamics unlike anything else in the solar system. But it's not just Uranus's orientation that sets it apart. Its atmosphere, composed mainly of hydrogen, helium, and methane, is a mystery. While methane gives the planet its distinctive blue color, the deeper layers and the processes that govern its behavior remain poorly understood. One of the most perplexing questions in recent years has been why the temperature of its upper atmosphere, known as the thermosphere, is steadily falling. The mystery of a cooling atmosphere. Uranus's thermospheric corona is a vast, thin layer extending tens of thousands of kilometers above the planet's surface. Despite being a staggering 2.9 billion kilometers, 1.8 billion miles, from the Sun, this region can reach temperatures in excess of 500 degrees Celsius, 932 degrees Fahrenheit. This has puzzled scientists because Uranus receives only a fraction of the sunlight that warms planets like Earth and Venus. When NASA's Voyager 2 spacecraft flew past Uranus in 1986, it provided the first direct measurements of the planet's thermosphere. These observations revealed surprisingly high temperatures, which were later confirmed by ground-based telescopes monitoring the planet over the following decades. However, a curious trend emerged from these continuous observations. Uranus's thermosphere was cooling, and its temperature had halved since Voyager 2's flyby. No other planet in the solar system shows such a dramatic cooling trend in its upper atmosphere. While natural cycles or external factors such as solar radiation could explain temperature variations on other planets, these explanations didn't apply to Uranus. Its cooling seemed to defy all known mechanisms, prompting researchers to search for a new explanation. Exploring the upper atmosphere. To unravel the mystery, scientists focused on Uranus's ionosphere, a layer of charged particles embedded in the thermosphere. This ionosphere is unique because it contains H3+ ions, a form of molecular hydrogen that emits photons in the near-infrared (NIR) spectrum. These emissions can penetrate the Earth's atmosphere, allowing ground-based telescopes to monitor the temperature of Uranus's thermosphere from afar. By analyzing decades of NIR data, the researchers confirmed that the cooling was not a temporary anomaly, but a sustained trend. Seasonal changes on Uranus, caused by its slow orbit around the Sun, were ruled out as the cause because the planet's seasons unfold over tens of Earth years, and the observed cooling didn't match these cycles. Similarly, the Sun's 11-year solar cycle, which affects solar radiation levels, showed no significant correlation with Uranus's temperature drop. The lack of clear links to traditional factors such as sunlight or seasonal changes led scientists to consider alternative explanations. The role of the solar wind. In 2024, a landmark study published in Geophysical Review Letters offered a compelling answer to the mystery. Led by Dr. Adam Masters of Imperial College London, the research suggested that the cooling of Uranus' thermosphere was linked to changes in the solar wind, a constant stream of charged particles emitted by the Sun. The solar wind consists mainly of electrons and protons, with traces of heavier ions. It flows outwards from the sun's corona at speeds of 300 to 800 kilometers per second, 186 to 497 miles per second. Although the solar wind is always present, its intensity can vary over time due to changes in the sun's activity and other factors. According to Dr. Masters and his team, the solar wind plays a dominant role in shaping the temperature of Uranus's thermosphere. Since the 1990s, the average outward pressure of the solar wind has been steadily decreasing. This decline closely mirrors the observed cooling trend on Uranus, leading the researchers to conclude that the two phenomena are directly linked. Magnetospheres and energy flow. Uranus's magnetosphere, a protective bubble of magnetic field lines surrounding the planet, is central to this cooling process. Unlike Earth's magnetosphere, which is relatively stable and symmetrical, Uranus's magnetosphere is highly asymmetric and tilted at a significant angle to its axis of rotation. This creates a complex interaction between the magnetosphere and the solar wind. As the solar wind weakens, Uranus's magnetosphere expands, reducing the amount of solar wind energy that can penetrate into the thermosphere. This reduced energy input leads to a cooling effect. Decreasing solar wind kinetic power, or nearly identical total solar wind power, should imply a weakening of the heating of Uranus's thermosphere, leading to the observed long-term temperature decrease, the researchers explain in their study. This discovery highlights a fundamental difference between planets like Earth, where sunlight controls atmospheric temperatures, and distant planets like Uranus, where the solar wind takes precedence. Implications for planetary science. The findings have far-reaching implications for our understanding of planetary atmospheres, both within and beyond our solar system. For Uranus, the study provides a new framework for understanding how energy flows through its complex magnetosphere and affects its atmosphere. This knowledge will be invaluable for future missions to the planet. The Planetary Science and Astrobiology Decadal Survey, 2023 to 2032, has identified a mission to Uranus as a top priority. The proposed Uranus Orbiter and Probe, UOP, would study the planet's atmosphere, magnetosphere, and interior in unprecedented detail. With the discovery of the role of the solar wind in cooling the thermosphere, scientists can refine the mission's objectives to investigate how this energy transfer occurs. Insights into exoplanets. The implications extend beyond Uranus to exoplanets orbiting distant stars. Many exoplanets exist in environments where stellar winds, analogous to the solar wind, could play an important role in shaping their atmospheres. For planets with strong magnetic fields and large magnetospheres, interaction with stellar winds could drive atmospheric dynamics similar to those seen on Uranus. Understanding these processes is crucial for identifying potentially habitable exoplanets. A planet's magnetic field is a key factor in protecting its atmosphere from being stripped away by stellar winds. By studying Uranus, we are gaining insights that could help us assess the habitability of worlds beyond our solar system, a planet of endless mystery. The cooling of Uranus's atmosphere is a reminder of how much we still have to learn about the outer reaches of the solar system. This enigmatic planet continues to challenge our assumptions, revealing new layers of complexity with each discovery. As scientists prepare for the next phase of exploration, Uranus promises to remain a source of wonder and intrigue. Its mysteries not only deepen our understanding of the solar system, but also inspire us to look beyond, to the countless other worlds waiting to be discovered.